All right, so we have discussed about the linear and the rotary displacement measurements. We have discussed a few of the can say instruments which are useful in the measurement of linear and the rotary displacements, which includes both the amount of displacement and also the direction of displacement, which is very useful for us and very important in our control purposes, in the monitoring purposes. So and obviously we have also seen that some of the instruments that are available to us have some limitations. ठीक है मुजम्मिल आप ये जो है ना इसका ऑफ करो स्पीकर तो है ना प्रपोजन ठीक है. So we have seen that each instrument has some let's say constraint in terms of its ability to measure the displacement, and also in terms of accuracy, in terms of the application where it can be used. And similarly, we have seen in the previous class about the rotary motion or the rotary displacement measurements, and also they also come up with some sort of, let's say, limitations. And now we are into the velocity and the acceleration measurements. So obviously in this also we do have the linear velocity and the angular velocity. So let's say similar to what we have in the displacement, and then the linear acceleration and the angular acceleration. So we call it translational or the linear velocity. So we do use some of the techniques to measure this let's say velocity, but mostly in the industries or in the application that we desire, let's say, we usually measure this quantity, let's say velocity, indirectly. So we do have some direct measurement techniques also available for the translational velocity, but most often the linear velocities are generally measured indirectly. So it could be similar. The first one could be the differentiation of the displacement measurements. So now we have seen we have some instruments that can be used to measure the displacement. So we can differentiate those signals. All right. So this differentiation can be done either inside the computer or the controller, where we make use of some techniques like finite difference methods, where we have the just try to sorry, where we make this displacements that we have measured. We calculate velocity, let's say in terms of let's say displacement values at time t1 and t2. So let's say if we call it as xt and xt minus 1 by, let's say, the total, so the time between the two samples that we get. So this would give us the velocity. So or else we have something seen in op amps also, or operational amplifiers, that we have a differentiator circuit, isn't it? I hope I have maybe talked about that differentiator circuit. So it's basically an op amp with some let's say the resistor and the capacitances that we have seen. So we have a differentiator circuit in which, if the input signal from the displacement is fed to the input of the op amp, so with different values of and combinations of the resistors and the capacitor, or the, you can see, passive components, you can get the velocity as the output. So this is one way where we can say that we have used an indirect measurement, because we are not directly measuring velocity, but we are directly measuring displacement, and velocity is in let's say a derived quantity from those measured parameters. But the issue with this is that you do get a lot of, let's say, noise due to the, it could be due to the errors in the position measurement itself, but those errors would generally get amplified when we do the differentiation process. Okay. So it means if there is small error in the xt signal that we have obtained, and also in the xt minus 1 signal that we have obtained, because it's divided by this sampling time, which is generally very less, let's say of the order of milliseconds, or maybe sometimes lesser than that. So that means if this t is millisecond, which means it's like 0.001 millisecond. So it means this xt minus 1 is actually getting multiplied by 1000, isn't it? Because 1 by 0.001 makes 1000. So whatever error was there in the xt signal, that gets amplified by 1000 times. So that's the problem with the velocity measurements with the differentiation. But we do make use of something called as filtering that we have seen, that we can basically filter out those signals at the displacement end only, or after even the measurement of velocity we can filter those high frequency noise that is associated with the signal. So for example, this is the input signal from the displacement, but if we see there is something like a noise present in this, so that means there's a spike in this form, which may be due to the hardware error or something like that. So there is, it has a good amount of frequency, this one, but what is happening, there is a small component whose frequency is very high or the time period is very low. So this means there's a big spike in this. So obviously if we measure velocity from using this displacement signal from here to here, obviously as two samples, so we get a correct output. But from here to here, when we measure the velocity, so we are actually getting the wrong value of the velocity. So and this amount, if it is of some units, it will get amplified by 1000 times if our time period or the instant between the two instances, let's say 1 millisecond, okay, between the two samples of the position measurement, then our the velocity error will get amplified by 1000 times, which is undesirable generally. So but this is used in several places. So we can say we make these we encounter these problems with the use of filters. But filters would give you a filtered output, but you have something called as attenuation or the delay that is associated with the filters. So suppose you have a signal like this as the input, so your output may be little bit delayed in terms of if it's a position xt that you are, this is the raw signal, xt is the raw signal and xt dash is the filtered signal, because you are trying to filter, let's say, position itself. You are, आप जो है एज्यूम कर रहे हैं कि हम पहले ही नॉइज को फिल्टर करेंगे पोजीशन लेवल पे ही, ताकि वो वेलोसिटी की डिफरेंशिएशन प्रोसेस में जाए ही ना। तो उसमें अगर हमारा ऐसा पोजीशन सिग्नल इनपुट है जो हमने मेजर किया, तो हमारा वेलोसिटी जो आउटपुट आता है जनरली फिल्टरिंग की प्रोसेस से इस तरह आता है कुछ. So this filtering process, sorry, it should be somewhere like this. So this filtering process itself incurs delay. So this is, we have got a now smooth signal, but what happens when we make use of controllers, when we have a plant, we have an output, and then we want to measure the output with the sensors, and we want to feed back it to the controller. Here we have a reference signal, this is the feedback signal, this is the error signal, okay? This is the output signal. So this is the sensor that we are using, this is the plant. Now the sensor is the instrument that we are using, all right? So if we have measured position, and then we are adding another component which is the filter, all right? So what happens is, for a good control, for a good control action, which means the getting stability, achieving stability in good amount of time or less amount of time, which is generally desired, it would also need that the sensor has to feed the information back to the comparator very quickly. But the moment you start putting up filters in between, so these filters obviously they do take some time to process the signal, which is obviously filters could be active or passive filters, where it needs to go through op amp and some resistors and capacitors. So this signal generally, or this type of filters generally incur some delay, and also some attenuation, means there is a decrease in the amplitude of the signal. Also this happens with the filters. And it's not just that we use a small op amp for this, we use something called as second order, third order, or fourth order. We have so many filters. We have Butterworth filter. मैं आपको इसका आइडिया दे रहा हूँ कि कैसे होता है. तो वी हैव चेबीशेव फिल्टर, इसमें जाने की जरूरत नहीं है, लेकिन ये है कि ये फिल्टरिंग प्रोसेस ही इतना अंदर एक ये आईसी होती है, इंटीग्रेटेड सर्किट होता है, लेकिन इसके अंदर जितना आप कट ऑफ फ्रीक्वेंसी जो फिल्टर्स में होती है, जितना उनको आप कोशिश करेंगे कम रखने की, या इस तरह आप जो है और भी पैरामीटर फिल्टर के चेंज करना चाहेंगे टू गेट अ वेरी स्मूथ सिग्नल, जितना आप स्मूथ चाहेंगे उतना आपका डिले बढ़ेगा. ये फिल्टरिंग थ्योरी में आप पढ़ सकते हैं, लेकिन नो नीड टू गो इनटू दैट दिस टाइम। बट जैसे हम फिल्टर जितना अच्छा यूज़ करना चाहेंगे उतना हमारा जो है नॉइज तो कम होगा, लेकिन हमारी प्रॉब्लम क्या होगी, हमारा डिले बढ़ेगा। सो दिस इज काइंड ऑफ, दिस इज वेयर द डिजाइनर्स और द रिसर्चर्स और यू कैन से द इंडस्ट्री में जो भी जाता है R&D में, रिसर्च एंड डेवलपमेंट, दे एक्चुअली प्ले विद दीज थिंग्स। दीज आर दी थिंग्स वेयर यू डू सम ट्रेड ऑफ, कि कौन सी चीज़ को बढ़ाना है, कौन सी चीज़ को कॉम्प्रोमाइज़ करना है। कहीं जगह पे थोड़ा सा नॉइज चलेगा, कहीं जगह पे थोड़ा सा डिले भी चलेगा, लेकिन किसी जगह पे डिले इंपॉर्टेंट होता है कि ज़्यादा डिले नहीं होना चाहिए, क्योंकि कंट्रोल लॉ पूरा जो है the whole plant will get unstable, so that you want to avoid. ठीक है। Second option for us is, let's say, is the integration of the output of the accelerometer. So we have accelerometers which directly measure the acceleration of the body to which it is connected to. So the accelerometers give an output in the form of a voltage which is proportional to the acceleration of that body. So once we have got the acceleration, so we can always integrate the acceleration, because acceleration is nothing but x double dot, let's say, if we understand it this way, or you can say theta double dot. This is the second order derivative of the position signal. So if we have x double dot directly with us, so we can integrate this back to x dot, and it can be further integrated to x. Similarly, theta dot and theta. So this process is sometimes comfortable, so it attenuates in even the noise and is therefore accepted. However, the absolute values are generally not available. So which means that if you want to calculate the absolute velocity or the instantaneous velocity, you may not be able to get that. You may get something like an average velocity over some time, a period of time, because of the process of integration, that we do associate something called constants with that can be solved if we know the initial value of the velocity or initial value of the position. So इसी तरह जो है जब हमें वेलोसिटी से अगर हम पोजीशन निकालना चाहेंगे, कि हमारे पास कोई जैसे वेलोसिटी मेजरिंग इंस्ट्रूमेंट्स अगर डायरेक्टली कोई अवेलेबल है, उससे हम पोजीशन निकालना चाहेंगे, तो उसको भी हम इंटीग्रेट कर सकते हैं टू गेट द पोजीशन सिग्नल। लेकिन उसमें भी क्या होता है, हमें पोजीशन जो है उसमें एब्सोल्यूट पोजीशन नहीं मिल सकती है, तो उसमें भी हमें यही जो रिलेटिव पोजीशन या कुछ एवरेज पोजीशन मिलती है। तो उसके लिए हमें क्या होना चाहिए पता, व्हेनेवर वी स्टार्ट सच इंस्ट्रूमेंट वी शुड नो द इनिशियल वैल्यू, then we can actually compare with that initial value, and accordingly those processes or those methods can also be used. And there is something called error accumulation because of the process integration that may also occur with the time. Then the third step could be conversion to the rotation velocity. So you can use something like gears, where you use a rack and pinion, where you have a rack which is kind of a moving linearly, but you can associate directly with a gear, where you can, rather than measuring the linear velocity, you can use the rotational velocity in measurement techniques that can be finally correlated to the linear velocity of that object. Okay, so these are some of the techniques or some of the methods that we use to estimate the velocity, translational velocity. Similarly, we have the rotational velocity. So we do have something direct measurements where we have tachometers, we have stroboscopes. Have you ever used this stroboscope या कुछ tachometer? आप में से कोई जवाब दो। कहाँ पे? मतलब किस एक्सपेरिमेंट में? कुछ बता सकते हैं आप क्या करते थे उसमें? मतलब आरपीएम। एग्जैक्टली। तो जायरोस्कोप की डिस्क पे हम एक मार्क करते थे, जैसे किसी पेपर से या किसी टेप से, ठीक है। तो अब जायरोस्कोपिक व्हील घूमता है, उसके बाद क्या करते थे हम, टैकोमीटर लाते थे। ठीक। अच्छा, कुछ आइडिया है कि कैसे काम करता था ये? चलो, आई थिंक विल डिस्कस दिस। बेसिकली जो ये ऑप्टिक्स पे ना उस प्रिंसिपल पे भी काम करता है, लाइट के प्रिंसिपल पे, जो हमारा जो रोटेट करता है जिस आरपीएम से, हमारा जैसे जायरोस्कोप जैसे एक कांस्टेंट आरपीएम पे मूव कर रहा है, और उसी हिसाब से जो हमारा जो लाइट सोर्स है यहाँ टैकोमीटर का, तो वो उसी हिसाब से जो है बेसिकली अगर जब तक वो उसकी फ्रीक्वेंसी के साथ मैच करता है, सो दैट इफ वी सी दिस एज अ स्टिल, इजंट इट? आपने देखा होगा एक्सपेरिमेंट, जब ये मैच करता है उसकी फ्रीक्वेंसी के साथ, तो हम उसको एग्जैक्टली ये हम स्ट्रोबोस्कोप भी यूज़ करते थे, हमने अपने टाइम पे स्ट्रोबोस्कोप यूज़ किए थे मुझे लगता है, उसमें हम बेसिकली इंक्रीज और डिक्रीज करते थे फ्रीक्वेंसी of the light that we would send as an input, and then accordingly we would see that piece of paper as standstill, kind of. So that concept is used in the measurement of the rotational velocity. Then we have mechanical fly balls. We have rate gyroscope that I'll be talking about. Then you have FOGs, fiber optic gyroscopes. These are the direct measurement techniques, and then we can again use in this case differentiation and integration of signals, that is position and acceleration. So we can positional जो हमारे encoders या कोई भी और इस तरह के instruments हैं उनको हम differentiate कर सकते हैं. We can get the velocity, and if we have the acceleration with the use of some accelerometer, so we can calculate the velocity by integration. ठीक है, so I have just mentioned there also integration provides the average velocity over time rather than the instantaneous velocity. मैं इसको बंद करता हूँ. So I'm just trying to maybe quickly recap I wanted to quickly recap the gyroscope also, because I hope it's clear to most of you, but still maybe a quick thing maybe will be necessary for understanding even the rate gyroscope concept. So let me draw a disk here. ठीक है, for example these are the axes. मेरे पास एक जायरोस्कोपिक टॉय था. आप लोगों ने जायरोस्कोपिक टॉय देखा किसी ने? हाँ, जो ऑनलाइन है वो बताएं. आप लोगों ने जायरोस्कोपिक टॉय देखा किसी में, आप में से किसी ने? मेरे पास था एक, मैं घर पे भूल गया वो. आपको इसी पे वीडियो भी दिखा देता. खैर, तो अगर आप ने जायरोस्कोप को पूरा अंडरस्टैंड प्रॉपरली किया हो, तो ये अगर हमें डिस्क इस तरह में दिख रही है, तो दिस इज दिस वन वी कॉल एज द स्पिन एक्सिस. ठीक है, this is generally called as the precession axis, and this is called the gyroscopic torque axis. जो हमारे सीआर हैं, जुबैर जरा आप बताओ, आप एक्सप्लेन कर सकते हो इसको, इफेक्ट को क्या होता है क्विकली, जो आपकी अंडरस्टैंडिंग है. जुबैर, बता सकते हो जायरोस्कोपिक इफेक्ट क्या होता है? बोलो. याद ही नहीं है तो मतलब समझा ही नहीं आपने. जरा आप में से कोई बताओ. मैं एक सेकंड एक वीडियो देखता हूँ जो मेरे पास अपना ही मैंने बनाया था. बताओ आप में से जिसको पता है वो बताए, कोशिश करें बताने की. मैं तब तक एक वीडियो देखता हूँ, इसमें है मेरे पास जो मैंने अपना खुद बनाया था. बताइए जुबैर, ये खावर, खावर जमान, जरा फिर से एक्सप्लेन करो. हम्म, एक सेकंड, बस एक वीडियो है, मैं देखता हूँ व्हाट्सएप आप लोगों में व्हाट्सएप में सर को एक बार भेजा था। देखो ये है हमारे पास एक टॉय जायरोस्कोप। जायरोस्कोप तो आपने देखे होंगे, but this is a toy gyroscope. This is how it looks like. So you have a gyroscope, you have some other instruments that are used to actually revolve this this disc about its axis. But I just wanted to show you a video. I had tried to make a video out of it. I don't know whether this should give you some good understanding. सोच रहा था यहीं पे आपको लाइव दिखा था मैं। Anyways, basically whenever जैसे मैंने कल कहा था, if there's a body which is moving linearly and you try to change its direction, so you need some force to change its direction, isn't it? Similarly, if a body is rotating continuously, ठीक है, and then you are trying to change its direction of rotation, or you can say the direction of motion of the axis of rotation, it will resist that change in the direction of rotation, ठीक है, or you can say the spinning. So we do make use of a spin axis, and where we rotate the gyroscope with some, let's say, motor, or we can even rotate it by some thread or something else, where we intend to actually make it move faster with let's say with some good RPM. Then the moment मुझे लगता है वो चल गया। See, I'm just controlling it on a robot, so it's not, the robot is not important here. The important is the gyroscope. It's a toy gyroscope. So I have brought it actually at home. So if you just see it clearly, this is the, are you able to see my cursor also moving? देखो ये अब दिख रहा है पूरा स्क्रीन। तो ये जो स्टील आपको दिख रही है एक्सिस, ठीक है, so this is the axis of rotation of this disc. This is continuously rotating, but this device, or this, let's say, spinning wheel is put up in some gimbals in such a way that it can, let's say, rotate about the other three axes also. So for a body in space, you can say that it can always rotate about three axes, isn't it? So let's say the first axis is the spin axis. That is about which it is rotating. Actually, it's a rotating one. You may not be able to appreciate the rotation of this, but this is rotating about its axis. So that is one axis. Another axis is, two axes are mutually perpendicular to that. Okay. The moment I am trying to change the axis with the robot, so it is kind of precessing. See, it's precessing about another axis. एक तो ये अपनी स्पिन एक्सिस के अबाउट रोटेट कर रहा है, लेकिन अब आप देखोगे जैसे ये मूव करेगा, अब ये एक और एक्सिस के अबाउट रोटेट कर रहा है. हालांकि दिस इज नॉट द एग्जैक्ट वे टू शो द प्रिसिशन, बट it is rotating even about another axis. So we do make use of or we do use this type of instruments to demonstrate these toys. तो इसके अंदर हमारा एक स्पिन एक्सिस होता है, एक प्रिसिशन एक्सिस होता है. तो अगर मैं यहाँ पे कोशिश करूँ इसको बनाने की, अगर मैं इसको साइड व्यू बनाता हूँ जायरोस्कोप का, अब जायरोस्कोप को मैं थोड़ा इस तरह माउंट करता हूँ, ये इस तरह, ठीक है, rather than mounting this vertically, I am putting it horizontally and I am trying to put this in some thread. आपने अगर ये देखे होंगे एक्सपेरिमेंट्स, मैं इसको थ्रेड के ऊपर बंद कर रहा हूँ, थ्रेड को सपोज मैं कहीं माउंट कर रहा हूँ. अब थ्रेड के अंदर इसको डाल के इसको मैं घुमा रहा हूँ अबाउट दिस एक्सिस. सो आई एम रोटेटिंग इट अबाउट दिस एक्सिस. So I am with some motor or with something else, I am rotating it. So I give it some angular velocity omega s, which is about the spin axis. ठीक है. So this, let's say, blue is the spin axis. अब आइडियली क्या होना चाहिए, अगर ओमेगा एक्स, अगर मैं कोई रोटेशन ना दूं तो क्या होना चाहिए अबाउट दिस पॉइंट, बिकॉज ऑफ द वेट ऑफ दिस डिस्क which acts in the form of W is equal to mg, ठीक है, which acts downwards. Because of this, W is equal to mg and some distance from here to here, ठीक है, let's say r, there is a torque, ठीक है, that acts about this axis, so which should actually make it move downwards. So this should actually fall down like this. So it should something like this. It should go down and then oscillate, let's say, if it's free to move. So this should happen ideally. Now the moment I start giving a torque, sorry, let's say a rotation to this spin axis and keeping it with, let's say, horizontally this way. So this disk, because of the rotation, develops an angular momentum because it has a moment of inertia associated with the disk. So that is, let's say, I. So I into omega s is the angular momentum that also acts in the direction of the omega s. So I omega s is the angular momentum which is, let's say, L. ठीक है, because omega s, if you see by right hand rule, ठीक है, so if it's rotated in this way, so omega s will point out in this direction, which is known as the spin axis. ठीक है. Now torque is continuously acting on this in this form at this point, so that is generally we write it as r cross f or r cross w. So that if you again take it by right hand rule, r cross f means you curl your fingers from r to f or r to w, your thumb should point in the direction of the axis of the torque. So it would be, let's say, clockwise because it's trying to move it clockwise, so it's something like this. So the thumb will point out inside. So let me draw with green pen the direction of the torque. So this is the direction of the torque which is acting on this because of the weight of the body. So which is torque, again is a vector here, so r cross, let's say, w. Okay, because of this torque this should go down, but because of the angular momentum here this doesn't go down but this moves around, let's say, it this angular momentum follows the torque vector, so it something like moves like this in this plane. ठीक है, समझ में आ रहा है? ठीक है, so it actually rotates about this axis, so which is, we add some, let's say, again velocities, which is omega p, which we call as the precession axis. So it precesses, that is the gyroscopic precession. So this we can say, this one, this was, can exaggerate it back, let's say this axis in the other direction also. So जो यहाँ पर ये आपकी जो एक्सिस है ये हमारी टॉर्क एक्सिस है, ठीक है, जो क्लॉकवाइज एक्ट कर रहा है. टी जो मैंने यहाँ लिखा, टी या टाउ एक ही बात है. So this is the torque axis, this is the spin axis, this is the precision axis. ये मैंने यहाँ पे दिखाया और ये डिस्क के हिसाब से दिखाया मैंने, तो एक ही बात है, यहाँ पर दिखाएं आप कोऑर्डिनेट सिस्टम या यहाँ पे दिखाएं. क्लियर? So this torque is equal to r cross w. All right, but we know that this torque actually is responsible for the precession. So what does torque do? So if there is no external torque like this, no gravity, if you mount the gyroscope in this way, let's say, and try to spin it as a spinning top, it will keep on spinning. Maybe it will not fall, it will not even tilt, but because of the non-conservative forces like frictional force and also the gravity acting on it, so what will happen is it will start precessing and then it will start, finally it will drop. But in this case the gravitational force is equally balanced from here and here, so it may not experience a torque in this form. But if you keep this gyroscope tilted this way, what is happening, because of the enough mass of the disk and the distance between the pivoting point and that mass which is located away from that point, you will experience a good amount of torque. Now this torque actually, or you can call it a gyroscopic torque axis, or you can say in gravitational torque that acts on this, is actually responsible for the precession of this gyroscope. Okay, so this gyroscope actually precesses. So even it is rotating about this axis, about its own axis, and also it's rotating about this omega p. So because of the rotation about spin axis, has an associated angular momentum which is I into omega, or you can say I omega s, which is the moment of inertia of this disk about its axis, and the spin angular velocity. This torque actually is responsible for what we call as change in the angular momentum. So what's happening is this is going in this way. Okay, and maybe we'll not be able to correctly show the disk, but let's show this omega s axis goes here. So to demonstrate, to understand this properly, let's assume this is a very small displacement, let's say, which is d theta, ठीक है, और P where it means it refers to precision axis, के about जो theta है. So this d theta P, and let's say this is now our another angular momentum. So this was our L1, let's say this is our L2. ठीक है. So this change in angular momentum is happening because of this torque, because torque is actually by definition change in the angular momentum. Force is change in the linear momentum. So now we can correlate these two actually to find out certain quantities. But to write it properly even, or maybe to correlate with the precision axis, we know that this d theta p, generally if you assume to be very small, it will approach to, let's say, you can say it approaches to sine theta p is equal to tan theta p. Can write it mathematically this way. So it's like perpendicular upon base. So perpendicular is nothing but L2 minus L1. So you can say L2 minus L1 by base is base, in the base we have L1. So the d theta p is equal to dl, which is L2 minus L1 by L, you can say L1 or you can say L initially. ठीक है. Now d theta p by dt will be the omega p, which is the angular velocity about the precision axis, or you can say the precision angular velocity. This is just velocity से precise करेगा. So that will be d1 by L, can write it mathematically this way, dl by dt. ठीक है, and it will be equal to 1 by L. What is dl by dt? It's nothing but tau. ठीक है, so this omega p will be equal to 1 by L tau. ठीक है, or you can say tau is equal to L into omega p. ठीक है, and L we know that L is I omega s, so we can say tau is equal to I omega s into omega p. ठीक है, so we can estimate actually the precision, the rotation of the about the precision axis by giving a particular amount of omega s using a motor, and obviously by designing a disk in such a way that is a particular moment of inertia. And obviously with motor we know this, and tau can also be estimated sometimes with this, because we know the distance between the two, we can get the angular velocity about the precision axis. ठीक है, or by giving some, or if the object is connected to this gyroscope in such a way that it precesses it by some omega p, we can estimate tau, and then accordingly we can correlate with the angular velocity with which it is being precessed, because accordingly it will also generate the tau. इसमें ये भी होता है कि अगर आप इसको प्रेसेस करेंगे तो ये एक टाउ जनरेट करेगा, एक टॉर्क जनरेट करेगा, उसको हम कहेंगे जायरोस्कोपिक टॉर्क. तो ये वाइस वर्सा है, या अगर आप जायरोस्कोपिक टॉर्क लगाएंगे तो ये प्रेसेस करेगा, और अगर आप इसको प्रेसेस करना चाहेंगे विद सम ऑब्वियसली सम टॉर्क, which means obviously with some angular velocity also, it will generate a gyroscopic torque which can be estimated. So this is how we can actually come up with the measurement of the angular velocity. तो इसीलिए ये angular velocity measurement में यूज होता है. अब जैसे मैंने कल बताया था, we have something called as free gyros, and we have restrained gyros. फ्री gyros क्या है? 3 जिम्बल लगे हैं हमारे पास, और उसके अंदर हमें रेस्ट्रिक्शन नहीं रखी है. तो आई कैन जस्ट मे बी ड्रॉ इट अगेन फॉर यू. थोड़ा समझ में आ रहा है कि सर के ऊपर से जा रहा है? कोई तो बोलो. जुबैर, हाँ
इसको अच्छे से थोड़ा
नहीं, तुम ध्यान से सुन रहे हो कि मुझे लगता है खावर कुछ उधर उधर का तो नहीं बोल रहा मैं? आया समझ कुछ? नहीं, कुछ अंडरस्टैंडिंग डेवलप हुई कि आपको पहले थी ऐसी?
सर 50-60%
अच्छा, मैं थोड़ा से रफ डायग्राम बना रहा हूँ, पता नहीं कैसे बनेगा, तो स्टिल आई ट्राई. तो ये हमारा स्पिनिंग व्हील है, ये हमारा एक जिम्बल है, जिम्बल मैकेनिज्म ना, which allows rotation with the use of bearings, let's say. So we have one axis is this, about the spin axis, ठीक है. Another axis is this, perpendicular to this. So this is the bearing here that allows the rotation about this of the whole mechanism. So this becomes our another axis, mutually perpendicular. And the third one is, somehow I'm not able to show it correctly, but it's somewhere here. It has to be something like this. Anyways, I hope you understand what I mean from here. It's not the proper isometric drawing, but something like this. So it can rotate about this axis, it can rotate about this axis, and it can spin about this axis. तो जायरोस्कोप इंस्ट्रूमेंट जब हम यूज करते हैं, ये बहुत ही मशहूर है, इनको कहते हैं हम इनर्शियल नेविगेशन सिस्टम. तो ये जहाँ पर जीपीएस, जहाँ पर बहुत सारे एयरक्राफ्ट वन प्लेस टू अनदर प्लेस जब जाना होता है, और अगर बिकॉज ऑफ समथिंग, if those systems are if those system collapse, or if you go into some tunnel or all such things where various things are jammed, or you go into those areas where jamming is there of the signals, the electronic signal from the satellites, inertial navigation systems actually prove to be quite handy, because they don't depend on any external signal, they depend on the way you are trying to actually measure. So you keep on putting rotating this spin wheel, जो हमारा gyro wheel होता है, उसको हम spin करते रहते हैं constantly से with some electrical मोटर, जैसे हमने डिस्कस किया था. तो एक डायरेक्शन में, तो हमें एक डायरेक्शन रेफरेंस डायरेक्शन बन जाती है. फिर जैसे हमारा एयरक्राफ्ट या हमारा जो भी डिवाइस है, जैसे वो मूव करेगी, तो उसी हिसाब से उस डिवाइस को हम फ्रेम के साथ अटैच कर सकते हैं, और हम उसकी जो है वेलोसिटी या उसकी पोजीशन मेजर, रोटेशनल पोजीशन मेजर कर सकते हैं. अब यहाँ पे क्या है, यहाँ पे चूंकि स्पिन एक्सिस एक तो स्पिन करनी पड़ेगी हमें कॉन्स्टेंटली, तो उसको तो वो तो हमारे लिए रेफरेंस बनेगी. तो हमारे पास बचे सिर्फ दो एक्सिस, 1 and 2. So we will use these two axes only in the measurement of, let's say, some let's say position. So because of this, we can only measure, let's say, two rotations with this one gyroscope. So if we have to use a free gyro, we have to use only, we can only measure once. Let's say this measures roll, and let's say somewhere about this we measure, we have some, let's say, scale, जितनी डिफ्लेक्शन होगी उतना हमें बताएगा कितना मूव किया. So this can measure, let's say, pitch, and this can measure roll, but for yaw we may have to use another gyroscope. So again, a similar one in the vehicles or in the aircraft also we use something called, this is typically referred to as the vertical gyro. So this measures the pitch and roll, whereas we have another one which is known as the horizontal one, in which the spinning wheel is, I'll just draw the spinning wheel. So it is rather than vertical, it is placed horizontally. ठीक है, बाकी जिम्बल्स आप इसको कनेक्ट कर सकते हैं. तो so in this case the spinning wheel is, the axis of the spinning wheel is horizontal, in this case it's vertical. So this is horizontal, or it's also called as directional gyro. And in this case it is again used for measurement of yaw, though we can measure another one also, because every free gyro we can measure two. So generally two gyros or two free gyros are minimum, two free gyros are to be measured, to be used to in the measurement of the three rotations of any rigid body in space. Similarly, we have the restrained gyros. ठीक है. So जैसे पिछले वाले में प्रॉब्लम क्या है, उसमें we because of the rotation about two axes we do encounter something called as drift, and because of the mixing of the information of one into the other, actually we have these problems of drift and other issues which has to be calibrated every time. So though we can have some automatic calibration of these also, but we do make use of something called as restrained gyros, which actually in which the one of the gimbals is actually restrained. So we say that the rotation of gimbals due to the precision, इसमें जो तीन एक्सिस है उसमें हम एक एक्सिस को लॉक करते हैं, precision of the spinning rotor is restrained by making use of a damper and a spring. So the rotation of the gimbal due to gyroscopic torque is the measure of input motion. I'll just explain it properly. So we have the rate gyro and the rate integrating gyro. Rate gyro is used to measure absolute velocity, and this is used to measure the absolute angular displacement. So now before going into its let's say mathematics a bit, we just take maybe 10 minutes. I'll just draw this on the figure first because that should maybe make it a little easier to understand. So for example, we have again a gimbal like this. And then we use a different pen. Zubair Alam. जुबैर आलम है लाइन में? कोई और आप में से है? मोहम्मद जावेद या तरुण कुमार? हाँ, समझ में आ रहा है आपको?
थोड़ा थोड़ा आ रहा है सर, लैग कर रहा है यहाँ पे सर, 2G के कारण थोड़ा थोड़ा लैग करता है।
अच्छा, चलो ये वीडियो सेव तो होगा बाद में।
यस सर, यूट्यूब पे सर अच्छे से देख लूंगा सर।
ठीक है, तो यहाँ पे हमारी ये एक एक्सिस है जो हमारे जो 3 एक्सिस होती हैं, एक इसमें ये वाली है, एक हमारी स्पिन एक्सिस है blue one. So obviously there was another axis which is perpendicular to the two, or you can say mutually perpendicular to the two. ठीक है? So let me make the complete diagram first. So this is the output theta x. Let's say this is the x direction. Let's say this is the y axis. This will be omega y. So the spin axis. Let's say this is omega z. This is the input. Now we make use of this. Maybe draw it here first. Spring and a damper, some stiffness coefficient and the damping coefficient. So this is how a rate gyro basically looks. All right, so what we are doing is sorry, we're giving input in the form of, let's say, precision here, and we're measuring the output, let's say, at theta on the other axis, because the spin axis is already defined. So we are giving input using a frame, let's say, that is connected to this, so that rotates this basically gyro about that axis. You can say about ओमेगा z जो है हमारा, ये हमारा इनपुट है, तो हम हमारा फ्रेम ऐसा है कि हम इसको इसके अबाउट रोटेट कर रहे हैं. इसके अबाउट जब रोटेट करें, समझो आप उस वाले जायरो में जो आपको डिफाइन किया था ये उसकी प्रिसिशन एक्सिस थी, लेकिन रादर देन allowing it to precise like that, so we are directly giving as an input to this in the form of rotation of that frame which is connected to this gyro, and it rotates it about this axis. So because the spin axis in this form, that will resist and it will produce some torque in this direction, and that is resisted by again a spring and a damper. So we can basically form or formulate a mathematical, let's say, basis for this. So we'll just write down these steps to be clear to us. So let's say if omega z is the angular velocity of gyro case, angular velocity of the gyro case, or you can say the frame about z axis. This is to be measured, and then we have the t or tau, which is the gyroscopic torque. This tends to rotate the gyro case through theta x about the x-axis, and this is, we have calculated it above, this is equal to the angular momentum into the we can write it here, I omega into omega precision, or we can precision here we have connected as z, and this can be let's say our omega z, omega precision spin axis का क्या है, omega y. So this will be I omega y, because I omega y is equal to L into omega z was equal to tau. We have seen that earlier. So after that we have where I is the moment of inertia of the disk about the spin axis, or you can say the y axis, and omega y is the spin rotation, or you can say angular velocity of the rotor. The output is theta x. So this can be basically measured using a pointer and a scale, or you can use some transducer again as an indirect measurement, give some voltage signal which can be correlated with the displacement. Now if in designing the gyroscopes, if we take, let's say, K as the spring stiffness, so we design these 8 gyros in this form, and C is the damping coefficient. So it's between gyro frame and the case. So we know that T is equal to I omega y omega z. This has to be equal to JD square theta x plus CD of theta x plus K of theta x. So what is this? This is nothing but the mass spring damper equation. So अगर आप यहाँ पे इसको कोरिलेट करेंगे, ये जो इक्वेशन मैंने लिखी, टॉर्क इज इक्वल टू आई ओमेगा वाई ओमेगा जेड, ये तो हमें समझ में आ गया, लेकिन ये जे डी स्क्वायर क्या है, डी इज नथिंग बट the differentiator operator, isn't it? So d square by dt square of theta x, so which is theta double dot x. So if you want, I can write it here also for clarity. So this is j theta x double dot plus c theta x dot plus k theta x. So what is this? Is nothing but spring mass damper equation, but this could be used for some rotational motion. So हमारे पास mx double dot plus cx dot plus kx होता था, वो होता था हमारा लीनियर डिस्प्लेसमेंट्स के लिए या हमारा रोटेशनल के लिए. अब ये कहाँ से आया, ये बेसिकली सिंपली वी कैन बैलेंस द फोर्सेस हियर. जब ये रोटेट कर रहा है अबाउट थीटा एक्स, तो जब ये रोटेट कर रहा है इस तरह अबाउट थीटा एक्स विच इज अबाउट दिस आउटपुट एक्सिस, तो ऑब्वियसली के एज पर द एंगल थीटा एक्स विल रेजिस्ट दैट, एंड सी थीटा एक्स डॉट. अब जे क्या है, जे इज द मोमेंट ऑफ इनर्शिया ऑफ दिस होल फ्रेम, दिस जिम्बल एंड दिस, let's say, spin wheel, everything about this axis, which can be, let's say, calculated if we want to design it as per our requirements. So j theta x double dot plus c theta x dot plus k x theta x will be equal to the torque actually that is generated because of spinning it, because of some body connected to this which is trying to spin it about this omega z axis, or you can say the z axis, and because of that some torque is generated, which we know that by gyroscopic principles that is equal to I omega y and omega z. So we can correlate this with this, and because of this we can get get a relation between theta x. If we take theta x common here, and we can maybe put omega z at the denominator, so we can see that it is equal to I omega y डिवाइडेड बाय, जैसे इसको राइट साइड में थीटा एक्स कॉमन निकाल के हम इसको इस तरह ऑपरेटर फॉर्म में लिख सकते हैं. सो वी हैव जे डी स्क्वायर प्लस सी डी प्लस के. So this will be JD square plus CD plus K, and this can also be put in the form of, let's say, Laplace transform, let's say S variable. So JS square plus CS plus K. So which means that we have now got a relation between the rotation which is to be measured. This is to be measured, and this is the output. So we know now we have a relation between output and the parameter which is to be measured. Okay, so this parameter obviously will be as per the rotation of the body, and we'll get an output corresponding to this in the form of this equation. Now so this is about the rate gyro, but if we, in this case, if we just remove this k, so we have a case if we remove the spring from this whole assembly. So if k is removed from this whole, so what do we get? So we get torque again is equal to I omega y omega z is equal to, rather than this we get j theta x, obviously simpler, plus c theta x dot. यही मिलेगा हमें, बिकॉज k तो है नहीं वहां पे, तो हमारा जो यहाँ पर अब रिलेशन क्या आएगा, हम इसको ऐसे लिख सकते हैं theta x dot. So we can write it this way if you want. So we can write theta x divided by, rather than omega, so you can say it is theta d theta by theta z by dt. Accordingly इसको हम निकाल सकते हैं. So we can have a relation between theta x and theta z, which is I omega y by, इसके अंदर एक ऑपरेटर हम इससे निकाल के हमारा ये बनेगा, सॉरी थीटा डबल डॉट के बदले हम, हाँ ये तो यहाँ ले लिया, हमारा जे डी आएगा प्लस सी, और यू हैव आई ओमेगा वाई बाई जे एस प्लस सी. ठीक है. So this is first order, this is the second order, because of the operator here available to us, because we can take a common differential operator also common. So because of that we will integrate velocity to position. So we have theta z and theta x from here common. So we get a relation between theta x and theta z, which means we have an input as the position or the rotational displacement, and the output again in the form of some voltage or some displacement of the pointer. So we have a relation between theta x and theta z. Now this is our rate integrating gyro. ठीक है. रेट जायरो रेट इंटीग्रेटिंग जायरो में यही फर्क है, इसमें हमारे पास स्प्रिंग नहीं रहता, एंड वी कैन कोरिलेट द आउटपुट टू द डिस्प्लेसमेंट ऑफ the object whose displacement is to be measured. And in the rate one, because of stiffness, we can correlate, because we have a relation like this, we can correlate displacement to the velocity or the angular velocity of this. So with rate gyro we can measure the angular velocity. With rate integrating gyro, where there's just a difference of removing that k, we can actually measure the angular displacement, and these are the absolute measurements only. And because of this we can measure only one. So whenever we use rate gyros or rate integrating gyros or rate integrating gyros, we measure velocity here, we measure displacement here. So we have to make use of 3 and 3. Let's say, for example, if I'm interested in velocity, so we have to make use of 3 rate gyros for the velocity or angular velocity about the 3 basic axes of any rigid body. Let's say yaw, pitch and roll, generally that we encounter in all these systems. ठीक है. सो ऑब्वियसली इनके अंदर भी जब डिज़ाइन हम करते हैं तो हमें क्या के लेना है क्या सी लेना है, इसके अंदर भी जैसे इस वाले सिस्टम में हम देखेंगे, रेट इंटीग्रेटिंग वाले में, सॉरी रेट जायरो में हम देखेंगे. अब हमें सी और के चूज करना है, तो डिज़ाइनर का क्या होता है, इसको क्या जायरो सिस्टम को बनाना. तो आपका जे भी आप बना सकते हैं, आई भी आप बना सकते हैं. आप डिस्क को ऐसा बना सकते हैं कि डिस्क जो है काफ़ी लोडेड, सॉरी काफ़ी हैवी होगी टुवर्ड्स द एंड, विच मीन्स हाई इनर्शिया ओमेगा, So you can accordingly define something called as sensitivity. You can also define some other parameters, for this type of systems. We have a thing called sensitivity. Check करता हूँ. Just to give you a flavor of this. So we do get, if we talk about the rate integrating gyro, let's say for example, where the equation looks like this. So we have the theta x is the output, theta z is the input, and we have an equation something like this: I omega precision divided by, sorry, I omega spin divided by the j d plus, let's say we had c. ठीक है, तो इसको हम मैथमेटिकली थोड़ा सा अगर जैसे इसको मैनिपुलेट करेंगे तो हमारा इस तरह भी एक फॉर्म बन सकता है इसको, बिकॉज ये हमारा फर्स्ट ऑर्डर सिस्टम्स का, अगर आपको याद होगा हम इस तरह लिखते थे, फिर के वुड डिफाइन दी सेंसिटिविटी, एंड सेंसिटिविटी के यहाँ पे क्या होगा, आई ओमेगा एस डिवाइडेड बाय, हम क्या कर रहे हैं इसको, बीटा, दैट इज द डैम्पिंग, तो सी बाई जे बाई सी. इसको अगर हम सी से डिवाइड करते हैं हर जगह तो हमारा सी से डिवाइड करेंगे ऊपर भी नीचे भी, तो हमारा आई ओमेगा एस बाई सी डिवाइडेड बाई जे बाई सी डी प्लस 1, ये हमारा इस फॉर्म में आता है, वेयर विच मीन्स आर के बिकम्स आई ओमेगा एस बाई सी. ठीक है, आई ओमेगा एस यानी एंगुलर मोमेंटम को भी हम एल भी लिख सकते हैं या एच भी लिखते हैं, एल बाई सी. इसी तरह हमारा जो टाउ होगा, जो यहाँ पर हमारा टाइम कांस्टेंट डिफाइन करता है, जो हमारा टाइम कांस्टेंट यहाँ डिफाइन करता है टाउ, टाउ क्या हमारा जे बाई सी. ठीक है, और तो इसको अगर हम जब डिजाइन करते हैं तो वी डू गेट सम इक्वेशन, दोस यू मस्ट हैव सीन दोस फर्स्ट ऑर्डर ग्राफ. हमें जो मिलता है, जैसे हम टाइम कांस्टेंट बढ़ाते हैं तो हम सॉरी टाइम कांस्टेंट डिक्रीज करते हैं तो वी हैव अ रिस्पांस व्हिच इज फास्टर. If time constant is decreased, we have a slower response, isn't it? But we have other issues as we play with these C and the stiffness. The sensitivity. So in this case, the sensitivity is K and the time constant is this. So इसका मतलब क्या है, अगर हम sensitivity बढ़ाना चाहेंगे इंस्ट्रूमेंट की तो हमें L बढ़ाना पड़ेगा. ठीक है, L बढ़ा सकते हैं. L में क्या करना है, हमें I बढ़ाना है. I तो हम बना सकते हैं डिस्क, लेकिन बिकॉज ऑफ कंस्ट्रेंट इन द स्पेस वी कैन नॉट गो फॉर एन इनफाइनाइट I. सिमिलरली ओमेगा इसको बढ़ाएंगे ज़्यादा तो वो भी अच्छा है, लेकिन उसके लिए हमें काफ़ी जैसे एनर्जी चाहिए इन द फॉर्म ऑफ इलेक्ट्रिकल एनर्जी टू इंक्रीज दैट ओमेगा एस. हम क्या कर सकते हैं, हम सी को कम कर सकते हैं. सी को कम करेंगे तो के बढ़ेगा विच इज़ गुड, लेकिन सी को यहाँ कम करेंगे हम तो हमारा टाइम कॉन्स्टेंट बढ़ेगा, तो वी विल हैव अ वेरी डिलेड रिस्पॉन्स. ठीक है, so these are some of the ways in which actually you play and then you actually try to trade off between the design of an instrument for a particular application. Similarly, जब हम इसका देखते हैं रेट जायरोस का, उसके अंदर हमारा के वाला पैरामीटर भी आता है, तो स्प्रिंग की स्टिफनेस को हम बढ़ा सकते हैं, कम कर सकते हैं, उसी हिसाब से उसका इम्पैक्ट बढ़ेगा हमारी इक्वेशन पे. तो ये हमारी इक्वेशन जो है, आपको इसका भी याद होगा, ये भी हमारा इस तरह आता था, जैसे इसका अंदर हम आई डोंट रिमेम्बर एग्जैक्टली, बट we would get a standard form for this, the second order standard form, in which we have the sensitivity, again we have the damping ratio, and we have the other parameters that we can actually play with by changing the J, C and K. But it's all trade-off that has to be taken care of as per the design requirements of the instrument. ठीक है, I think this is it. You must be bored also and then tired also. If you have any query, I can quickly take up one and then we can exit. किसी को कोई डाउट ऐसे जनरल?